So exponential functions. Last thing we're going to look at is financial applications, right? So a lot of the applications of exponential functions are population growth or growth in money. So one of the things with money, involving money, is compound interest. So if money is invested in a compound interest account, so everybody know what interest is? So interest is either, if you borrow money, interest is the cost of borrowing. It's what you pay the bank to borrow the money. So you repay more than you borrowed. And if you're depositing money, then they will pay you interest on the account, which these days is pretty darn close to zero interest. So they,
1 cent.
1 cent in interest, probably from the entire month. Like in this month, I earned 1 cent in interest. So in a compound interest account, interest is earned on the original amount as well as on any interest that is accumulated over time. And this is often paid over different time periods. So the one we're going to look at here, if you invest $1,000 for 4 years at a rate of 3%/A, so that's short for 3% per annum, which comes from Latin for annual, right, which is a year. So 3%. So when you see /A, it's per year. Okay. Compounded annually. Compounding period is how often they pay the interest. So in this case, the interest would be paid every year. So you've got the $1,000. You know, you could buy a bond or something like that, or it could be in a GIC. There's $1,000 there. It earns 3% interest. So if we look, you can set up something like a spreadsheet here. So year 0, I put in $1,000. It earns 3% interest. So 3% as a decimal. So interest rates are expressed as percent, but they have to be converted to decimals. And the way we do that is we just divide by 100. So 3% is 3, right? I mean, percent just comes from French for out of 100. So it's 3 out of 100, and that's 0.03. You just have to watch when you're dividing on your calculator. What would 0.3 be as a percent?
What is 30%?
Yeah, 30%. Right? So 0.3. So to convert a decimal to a percent, we multiply by 100. 0.3 times 100 gives us 30%. So when you've converted to a percent, just make sure that you actually have it as a percent and you're not 10 times bigger than you should be or 10 times smaller.
Started the whole market.
Oh, sorry.
Looking for these. Went into the math office.
You're on YouTube now too. Okay, so 3%. So 1,000 times 0.03, which is $30. The ending value, so at the end of the year, they pay you that 30. You now, in your account, have $1,030. If we do this exponentially, right, we're growing by 3%, so it's 1,000 times 1.03. So the 1 is what keeps the 1,000. The 0.03 is what gives the interest, right? So if we look at 1.03, doing what we did the other day, 1.03, we would subtract 1, which would give 0.03, multiply that by 100, and get 3 and change it to a percent. To change the percent into this decimal, we divide by 100, get 0.03, and then add 1 to it, okay, to get it in the form for our exponential. So that's at the end of the first year, so year 0. At the end of that year, we have 1,030. So our starting value the next year is 1,030. We have 1,030 times 0.03. Get the calculator up and running. So 1030 times 0.03. Gives us $30.90. So basically, we know the original 1,000 is earning $30 in interest, and this $30 must be earning the 90 cents then, right? Our ending value would be, so we're going to add these two guys together, get 1060.90 And in exponential form, we're going to multiply by 1.03 and then multiply by 1.03 again. So it'll be 1.03 squared. We then go down. So actually, I'm going to add the 1030. Okay. So at the start of the next year, instead of the 1,000 that we had initially, or the 1,030 that we got after the first payment of interest, we now have 1,060.90. So it's 1060.90 times 0.03. So up here, just going to go times 0.03. So we will earn this time $31.83. So $31.83 in interest. Now, what I'm going to do is switch this to a mode that has 2 decimal places so that all the rounding will happen for us. So you go to mode, go down to float, go over to 2, just say show me 2 decimal places, and then I can just go second function quit, just get out of this, which apparently I can't. Second quit. Okay, and then from now on it will it'll round. So if I add on the 1060.90, so what I'm going to do is take this number here, that, and go plus, and take this number here, and when I hit enter, it'll round it to 2 decimals. Okay, so we now have 1092.73. And we'll multiply by 1.03 to get here, this amount by 1.03 to get here, this amount to get the third amount, 1092.73. That now becomes our new starting value. We then take 3% of it, 0.03. Usually we don't bother with the interest earned column, right? But we don't care how much interest earned, we care what is it worth now. Okay, and that's what we get in this column, the ending value, right? What's it worth at the end of the year? But here, so we're just going to go times 0.03. This time it's going to round, so it's $32.78 in interest. Add those 2 numbers together, so I'm just going to go plus. So the plus will pull down the 32.78, and I'll just pop up and bring down the 1092.73, and we have $1,125.51. And that would be the 4th time that we multiply. So that's now our new starting amount. We have $1,125.51. We multiply that by 0.03 to find out how much interest we earn. So $33.77 in interest this time, $33.77 plus, and then we add on the amount we had there, starting amount for that year, and we get $1159.28. And that's 1,001.03. So the formula for calculating compound interest. A of n, which is the future or the ending value or the accumulated amount, or just the amount. The amount we're going to end up with is the amount we started with. So P is the principal, which is the amount invested. How much did we invest? N is the number of times the investment is compounded, this N. How many compounding periods? So we call that compounding periods. Compounding periods. And a compounding period is just how often you're paid the interest. So if it's annual, you get paid the interest every year. If it's monthly, you get paid the interest every month. I is the interest rate per compounding period. So N is the number of compounding periods. I is the interest rate per compounding period. So we have to do different stuff depending on our interest rate and our compounding period. So let's take a look. We got $5,000 is invested. I'll leave this so we can see the bar. $5,000 is invested at 6% per annum, so 6% per year. Interest rates are always given as yearly. Okay, they're always given as how much per year, but the compounding periods differ. So calculate the ending amount if the interest is compounded annually, so once a year. So then we don't have to do anything special in the formula. So A of n is our $5,000. Well, we're going for 4 years, sorry. So we could say A of 4. The amount after 4 years is the $5,000. 1 plus I. Okay, so our interest rate is 6%. So 1 plus 0.06. That's got to be converted to a decimal. Okay, otherwise you'd be getting a really nice interest rate of like 600% to the power of 4 because we are doing it once a year for 4 years. Okay, go to the calculator. Go to that. So go 5,000 bracket 1.06 to the power of 4. And we hit enter and we see we'll have $6,312.38. So 63.12.38. So annually, once a year, interest rate 6% per year. So we get that 6%. We get it once a year and we do it for 4 years. Semi-annual, right?
In the first one, where it says that exponential form of the separation of the table, we spent like 1,000 and we had 1.03, we had 1.03. Why in that one, in the second one, we did 1 plus 0.06. Like, could we make it the second one?
Okay, which one?
1.06. Talk about how in the first question, the equation is the equation,
6%.
I'm not asking why, that's why you did the 1.
Oh, in the exponential form of the calculation, the one, he's asking why there's a 1 before the decimal.
Oh,
I know 1 plus.
yeah, 1 plus the interest rate, which is 3%.
Yeah, so for the 1, you have to do 1 plus, but then you automatically do 1.06.
Now down here. Oh, you could just, so I'm showing you 1 plus I because that's what's in the formula. Okay, and it's going to start changing, so that's why I'm doing that. Okay, there's a reason, trust me. I hope you fast forwarded through the last 3 minutes if you're watching. Semi-annually. So how many semi-annual periods are there in a year?
There's 2.
Two.
Semi is half.
Yeah, or it's a big truck, but I guess we'll go with half. Semi. So a semicircle is half a circle, right? So semi-annually is 2 times per year. So interest is compounded semi-annually 2 times per year. So here's what we have to do. So if it's once a year, we get 6%. If it's twice a year, we don't get that 6%, right? We get half of it. So it becomes A, I'm just going to go with A as the amount, is 5,000. 1 plus, so here we go, 0.06. It's semi-annual, so we're going to divide the interest rate by 2. Okay, because we get paid twice a year. So what happens is, every 6 months, semi-annual is every 6 months, every 6 months we'll get 3% interest. Okay, but we get it twice a year, so this becomes 4 times 2. So 4 years, but we're getting paid twice a year, which is 8 compounding periods. Right? So if we get paid twice a year for 4 years, then we get paid 8 times. So think about it, you put the money in January, at the end of June, you're going to get paid interest, right? But not 6%. 6% is for every year. You're going to get, so there's a reason, that's the reason why I wrote it as 0.06, so I could divide it by 2. Yep.
Still technically getting 6% data, right?
Actually, let's see what it works out to. So 0.06 divided by 2 is 0.03, so this will be 1.03, and 4 times 2 is 8. So let's check that out. So 5,000, 1.03 to the power of 8. So now, instead of $6,312.38, if we get paid the interest twice a year, we end up with $6,333.85. So in essence, you're getting more than the 6% a year. Okay, and the reason is, after 6 months, if you have $5,000, they're going to take that first chunk of interest and they're going to put it in with the 5,000. So for the second 6 months, when you earn that 3%, it's on a larger amount of money than you had in the beginning. Okay, if it's once a year, it's only that 5,000, that gets the 3%, and we're done. Okay, but with compound, so it's called compound interest. You earn interest on the interest. Okay, so they pay you out the interest at the end of June or whatever, 6 months, and then you earn 3% interest on that higher amount for the next 6 months, and we end up with, what, about $20 more. So what if we go quarterly? How many times a year is quarterly?
4 times a year.
Yeah, 4 times a year, right? So 4 times per year. So now the amount is equal to the principal. So we got our $5,000. 1 plus, okay, the interest rate is 0.06. But if you're getting interest 4 times a year, you don't get 6% each time. That'd be like 24%. You get 1/4 of the 6%. So we write 1 plus 0.06 divided by 4. And we do it for 4 years, but how many quarters are there in 4 years? 4 per year, right? So then we take the number of years 4 and we multiply it by the number of times per year we're getting paid. So basically what we're doing is we're cutting the interest rate by however many times we get paid, but we're increasing the number of years by that same factor. So you're going to divide interest by 4, but you're going to multiply the number of years by 4 to make up for that, because you're getting it 4 times a year. All right, 5,000, bracket, so I 1 plus, so I'm just going to go 0.06 divided by 4. Okay, so I don't have to worry about working that out. So I can just say 1 plus 0.06, my interest rate, divided by 4, to the power of, so we know it's 16, but we could just go 4 times 4. Now, if you have an older calculator, when you go to the power of, just go bracket, 4 times 4, and then close the bracket. So we should expect more than the 63, and we end up with 6344.93. So 6344.93. So about $32 more than annually, and about $11 more than semi-annual, or sort of then quarterly. Monthly, how many times a year would you get interest if it's monthly? So 12 times per year. So 5,000. 1 plus, so I really don't want to work this one out. Okay, I mean 0.06 I could do 0.015, but it's kind of like, why bother? We're just going to enter it. That's why I did that with 1 plus 0.06, because we have to adjust this. To the power of 4 times what? 12. So 12 times a year, divide the interest rate by 12, multiply the number of years by 12. So we're going to get whatever 0.06 divided by 12 is, to be a much smaller number. We'll get that amount of interest, but we'll get it 12 times a year for 4 years, so there'll be 48 times. Okay, now I'm just going to go 5,000. 1 plus 0.06, okay, divided by 12. So you divide the interest rate. Interest rate's got to be a decimal, right? 6% is 0.06. To the power of 4 times 12, which is 6352.45. So $40 more than annually. Okay, $19 more than semi-annually, $8 more than quarterly. What if we did daily? Like, how much money can we eat daily? So daily is how many times a year? Yeah, so 365 times per year. All right, see if you can work it out. So write it down, 5,000, etc., etc. I'll pause. Okay, so daily, 1 plus 0.06 divided by 365 to the power of, and it's 4 times 365. So we're dividing the interest rate. So let's try that, 5,000, bracket 1 plus. So this is one you really don't want to work out, right? Because it would be a lot of decimals and you'd have to copy them all in. So just let your calculator do it here. 365 to the power of 4 times 365. And as you said, $6,356.12. So $4 more than monthly, and how many? $44 more than annually. If $4,000 is invested at 8% per annum, so 8% per year, but it's compounded quarterly, determine, what does determine mean? Show your work. Determine how many years it will take for the investment to double. Okay, if the investment's going to double, how much money are we going to end up with? $8,000, right? Okay, got our formula. A is P1 plus I to the N. So I'm just going to write the formula down because we're doing something we haven't done before, right? And then we're going to substitute into the formula. So how much do we want to end up with? 8,000. How much did we start with? 4,000. What's our interest rate? 0.08. And it's compounded quarterly, right? So we got to take our interest rate 1 plus 0.08 divided by 4. Now, we have a couple of choices. If we just put an N here, it will be the number of quarters. Okay? It'll be how many quarters. Then we work this all out. We get our answer in quarters. We divide it by 4. We can change it to years. Or you could put a 4n up here. And then when you solve for n, it will be in years, right? Because we'd have to take the years and multiply by 4. Okay, so which one do you want to do? Your choice. 4n. 4n? Okay. So, it says quarterly. We go 0.08, interest rate 8%, as a decimal, 0.08, 0.08. Divide by 4. Years, n, get multiplied by 4. Okay, now we can simplify this. We could divide both sides by 4,000. Now the only way we can solve this is to put it into our graphing calculator and solve for n, or x, right? It'll be x. We have no other way to do this, right? We don't know how to solve for an unknown exponent. Okay, let's just go here. We'll go to y equals, clear out what's in there. So I can put the 8,000. Then the next line, I'll put the 4,000, bracket 1 plus. Now, you can either do this in your head, 0.08 divided by 4 is 0.02, or just enter it, 0.08 divided by 4 to the power of 4x. So when we solve this for x, we will get the number of years, right? We'll go directly to the number of years. If you just put an x there instead of a 4x, you'll get the number of quarters, right? It'll be the number of compounding periods. And if you got the number of quarters, you would have to divide that by 4, right? If you got 48 quarters, then you would say that would be 12 years, right? 48 divided by 4 is 12. But here we will solve directly for. Okay, I don't know how many years this is going to take, but we'll set our window to go 0, I don't know, let's say we give it 20 years. Go by 1 is okay. And to go from 0, we want to have 8,000, so I'm going to put in 10,000, and we'll go by thousands. Okay, so I'm okay with that. We have nothing in the tables. We don't want our stat plot on. If I have my stat plot on, then it's going to give me an error invalid dimension, and I'll just have to go into second y equals and turn it off. Let's just hit graph, see what happens. So, looks like I might have some points sitting up here, but okay, so we're good. We just need to find out where they intersect. So I'm going to show this. So y1 is 8,000. y2 is 4,000. 1 plus 0.08 divided by 4 to the power of 4x. My x window, I said, was 0 to 20 by 1s. My y window was 0 to 10,000 by 1,000. The graph looks like this. There's y1. There's y2. We're going to go second count intersect. So we're interested in the x coordinate. We know the y value, it's 8,000. Right? We're interested in the x. That'll tell us how many years. Intersect. 1, 2, 3, and 8.75. Okay, so 8.75 years. So if we were rounding, it says how many years will it take, then how many years would it take? 9 years, right? We're going to have to go up to the next full year. So it would take 9 years. Take 9 years to double. Okay. That's at 8% interest, right? 8% compounded quarterly, 9 years. Table below shows the value of an investment with respect to the number of years it's been invested. State the equation of the exponential regression function that models this situation. All right, yay, right? Time to practice an exponential regression. So let's go to y equals. Y equals. Let's just clear out whatever's in there. So it's good just to clear your calculator out. Let's go second mem, the plus sign, to number 4, clear all lists. I don't know if there's anything in there, but I just want to get it out of there if there is. Then go to stat and edit. Make sure you're in L1. So in L1, we're going to put 0, 1, 2, 3. So 0, 1, 2, 3. You notice mine's rounding to 2 decimals because I told the calculator earlier to round to 2, which I think is fine. Because we're dealing in money, and money is always usually rounded to 2 decimals. So $600, 626.40, 653.96, 96, and 682.74. Okay, so give everybody a chance, make sure you've got all those numbers entered. And always double check them, right? If you're running any regressions on quizzes or tests, always double check. Make sure that they're entered correctly, especially running regressions, because you put a number in wrong, then your regression is wrong. Everything you answer from that point on would then be wrong. Okay, we go to stat, over to calc. Now either we remember it's a 0. If it's not on the screen, it's easier to get there by arrowing up. So we go to exponential regression. Okay, and now if you're looking at exp-reg on the older calculators, you're just going to go vars, y bars, enter, enter to get the y1. If you're looking at this, you want to store the regression equation. And we can also do alpha F4 and then hit enter. You want to save one keystroke. So either we're looking at expreg space y1, or we're looking at this screen. Hit enter to calculate. On yours, just hit enter, it'll calculate. And we get y is equal to a 600.001.04 to the x. So state the equation just means write the equation down. Okay. Really, probably should have said round your values to the nearest 100. What is the annual interest rate that's being paid on this account? How much? 4%, right? So what do? We go 1.04 minus 1 is 0.04. Take 0.04 times 100, turn it into a percent, 4%. Okay, you can just state that. You can just state that. Okay. You don't need to, I didn't say determine or anything. What would be the value of the investment after 10 years? So, easiest way would just be to go to the graph. So we've said put it in Y1, right? So it's sitting there in Y1. Now my values are all rounded to 2 decimals because I told it to. Go to the window and just say, okay, let's go 0, let's go past 10, so let's say to 15 by 1. We know it started at 600. I don't know where it's going to end. I like to start at 0. And let's just say 1,000. And we'll go by 100. Okay, and hit graph. So now we get the usual where we see the points, right? We see this, because I got my stat plot on, so we're seeing the points. And then go second, calc, and well, it's not second. We go second, calc, and value. Okay, we want to put in an x value of 10, and we get a y value of 888.15. So 888.15. So we got that off the calculator. Now the calculator is carrying more decimals. I just happen to set this to round 2 decimal places. So when I do this, using the round end, we get the same value because it's rounding. Okay, if I go back to mode and go to float, float. Then let's see if I rerun the regression. Yeah, so stat, calc, exponential regression is 0. Store regression equation, vars over to y vars, enter, enter, put y1. So now it's 599.999, etc. If I go, sorry, let's do that. If I go into the table, it's a different value. So if I graph that, hit second calc. Okay, second calc. Try again. Value. And put in 10. So now we get 922.92. So moral of the story, if you're running regressions, don't have your calculator set to round things. Okay? So when you're running a regression, do not use a rounded value. So that goes bye-bye. You can round when you're writing out the equation. Okay, so if we go here, so I would round that to 600 because you can't do much with 599.999. So 600, but it's 1.04. I think it was 1.044 to the x. So even if we were rounding like that, if you use that, you'll get 888.15. If you use the actual regression, you get 922.92. Okay, they won't both be right. What you want to do is you don't want to use the rounded values. Okay, so whenever you run regressions, make sure your calculator, the mode, is in float and not in a rounded. It's time to pay off the loan. Bankers will calculate how long it will take you to pay off the loan given the interest rate, the amount you are borrowing, and your monthly payment. So Jamie borrowed $7,500 from the bank to buy a used car. The bank is charging an interest rate of, good luck getting 3.6% per annum, but the bank is charging an interest rate of 3.6% per year, and it's compounded monthly, and she's going to make monthly payments of $400 a month. Okay? So borrowing $7,500, has to pay interest on that. This equation will model how long it takes to pay off the loan. Okay? Really weird equation. Your bank is not going to hand you that. Usually they would just do a spreadsheet and say, okay, you're borrowing $7,500. So generally what happens is you get the $7,500 at the beginning of the month, and you make your first payment at the end of the month. So what they do, take the $7,500, they add on the interest to it, and get that new amount at the end of the month, and then you pay $400. So at the end of the month, you actually owe more than $7,500. You owe the $7,500 plus the interest. Then you pay $400. They take that new amount, it earns interest for the month, they add that on at the end, you pay $400, and it's just kind of dance between, goes up a little, and then drops 400. Goes up a little, and then drops 400. Well, this is going to tell us how many months it will take to pay off. So we're going to go y1 is 1.003 to the negative n, right, or negative x. We can't do an n. And y2 is 0.94375. Okay, so we're in float. Make sure that it's in float mode for doing this. Go to y equals. Let's clear that out. You know what? I'm going to clear all the lists, although we're not actually running a regression, but I'm going to clear the lists. I'm also going to turn off the stat plot because we're not running, so that's off. And okay, so everything's clear. There's no data sitting in the table to be graphed or anything like that. We go to y equals, put in 1.003 to the power of, okay, older calculator, you're going to go bracket negative x. Okay, so negative x. Newer calculator, if it's up there, you can just put in the negative x. Okay, and y2 is 0.94375. Now, let's just kind of figure out how long should this take to pay off, right? So $7,500, let's call it $8,000, and you're paying $400 a month. That would take about 20 months, right? So for $8,000. So when I'm going to set a window, we'll say, all right, let's try 20 months. 20 by 1. Now, this number is really very specific, right? Like it's 0.94375. It's given to like 5 decimal places. So I don't want to just graph like 0 to 10 or something, right? Or 0 to 1 even. I actually do want to get really close to this number. So I'm going to go from 0.9 to 1.0. Okay, so I'm keeping my window to 1/10. It's just very tight around there. So this will be in the middle of the window, right? 0.9 at the bottom. So 0.9 at the bottom, 1.0 up top. This line is a flat line will run like this. And that means all we might see is we're just going to see a little tiny slice of this guy here. Okay. So 0.9 to 1, and then we'll go by like 0.01, just so there's like 10 of them. Hit graph. Okay, so there's the exponential function, which is actually looking like exponential decay. And there's the amount that we, this amount here, and it is pretty close to 20. So second calc, we want to intersect, and I'll toggle that on. And I'll toggle that off. And go 1, 2, 3. It says 19.32. Okay, so give the details. Right? We're looking at this and this. That's 19.32. Well, 0.33, I guess. We're going to the 100. This is y1. This is y2. Our x window was 0 to 20 by 1s. Our y window was 0.9 to 1.0 by 0.01. Okay, and there's our graph. So if you're doing something graphically, show what you're doing, right? So that if I'm up there marking and you've done something and it's graphical, then, and I'm like, what's going on here? I should be able to duplicate your graph, okay, see what's happening. And when we're figuring out the window, right, like just take, that's why I said 20 was, well, let's go close to $7,500, but you're going to owe some interest. So that's why I said take 8,000 and divide it by 400. If you're paying off a house or something, you know, you might be paying off $400,000 and you're paying whatever, $1,000 a month. Like houses take a lot longer to pay off. Okay, so in months, you might not be looking at, oh, let's just go to 20 months, right? You might be looking at, let's go to 200 months or 300 months. Or, you know, it could take 25 years to pay off. That would be 300 months. Okay, so there's a question in the book that does ask about a mortgage on a house. Right, and then just be aware. Well, yeah, it's not going to pay off in 20 months. It's not the $8,000 you're borrowing $400, right? So now the question is, how much interest will she end up paying on the loan? Now, in real life, what would happen is she'd make 19 payments, and then the rest would just pay off in a lump sum. You'd pay in the last month. So in 19 months. You would either pay off the 400 plus whatever else was owing, just so you're done. End of the month, here's 400, and then there's another $30 owing, here's the 30 bucks. Or you'd make that payment, and then in the last month, you would not be paying $400. You'd just make a last payment, which would be less than $400. Right? So when it comes to the end of the loan, then you make a decision as, yeah, I'll just pay it off this month, or next month I'll just pay off whatever's left, right? And that won't be costing that much interest. But here's the question. How much interest will she end up paying on the loan? So we're going to say, well, pays $400 a month, right? For how many months? Well, let's say for 19.33 months. Actually, we have the number sitting there. So we'll pull the number out, the actual number. So I'm just going to go like ... So 400, and then X was the number of months. So 400X. So total amount that she paid back to the bank was $7,730.77. So how much interest did she pay? Yeah. So from that, we're going to subtract, well, she borrowed $7,500. And we're just going to subtract, and we get $230.77. Right? So you're paying so much per month for that many months, and we'll just go with the 19.33. Just to, okay, you're just going to pay it off at the end of that month. The 19th month, you'll make a bigger payment. So $400 a month for 19.33 months amounts to $7,730.77. She borrowed $7,500, so you subtract the amount that was borrowed from the total amount paid back, and that $230.77 is the amount of interest, right? That's how much interest had to be paid. Okay, so we're done, but I want to show you what exponential growth really does. Right? So we know that, you know, like nothing much happens, but then it starts to do this, right? It starts to go up. So we've seen the graph. So here's a question for you. So don't do anything on your calculator. I just want you to. So let's pretend 1,000 years ago, 1,000 years ago, you had an ancestor who put away 1 penny, $0.01. They put 1 penny in the bank at 4% interest per year. 4% slashing. Okay, it is now 1,000 years later, and the money is yours. How much money do you think you'll have? Okay, so one more time. You got 1 penny, 4% interest per year for 1,000 years. How much money?
$400.
$400. Okay, anybody else got a guess? 1,000 years. 4%. I don't know what your calculator is. Take a guess. Take a wild guess. Go ahead, wild guess. What's a wild? Yep. $4,000. Wilder guess. What's a wilder guess?
$40.
40. Huh?
$40.
$40. We're stuck on fours.
400,000.
400,000. 800,000. All right. Well, we can figure this out.
Actually, I have one. What is X? $63.
Okay, so here's the formula, right? The amount is the principal. So the amount we're going to end up with is, and we'll do it in dollars. So $0.01. 1 plus 0.04. We can just go straight to 1.04 to the power of 1,000. Right? That's how many compounded digits. Okay, work that out. Let me know. What's the answer? 0.01. How much will that 1 penny be worth? And your answer will be in dollars, right?
1.07978994.
So that's 1.08 times 10 to the power of 15. So 10 to the 6th is a million. You guys never even really got close. 10 to the 9th is a billion. 10 to the 12th is a trillion. 10 to the 15th is 1,000 trillion. Let's call it a quadrillion. So you got a little over $1 quadrillion.
So the closest.
Yeah, I was the closest without going over. You could have guessed 200 billion and been the closest without going over. But here, so I did this on a spreadsheet. So here's year 0, you have 1 penny. In 50 years, you have 7 cents. In 100 years, you have 51 cents. In 200 years, you got 25 bucks. 250 years, you got $181. In 500 years, you actually have some real money now. You've got $3,286,000. Here's the graph, right? Now remember, this is 1 times 10 to the 15th. So this is 0. This is 2 times 10 to the 14th. So nothing much happened, right? Like the graph doesn't even really move until we hit about 900 years. And then on this scale, right? On this scale, the graph isn't moving. Like, you know, even $1 billion at year 650 doesn't show on this scale because $1 billion is just 10 to the 9th. That's 10 to the 14th, right? That's 10,000 times more. So it just doesn't show. That's what an exponential growth looks like, right? Nothing happens and then, right? That's what we want to avoid with this disease, right? It's like, oh yeah, this. But then, that's what happens. All right, there's another scenario on this spreadsheet. 2 brothers, Amos and Andy. And I think they start, I forget the exact age, but let's say they want to save for their retirement. So one of them, I can't remember which one, but I'll look at it. I'll bring the spreadsheet up. One of them puts away $1,000 a year from the time they're like 20 to the age of 35. Okay, $1,000 a year each year from age 20 to age 35. The other one starts at 35, puts away $1,000 a year until they're like 65. Okay, so when they're 70 years old, who has more money? And here's the assumption: we're going to assume it's 10% a year in interest. That's not wildly outrageous. The S&P 500, the stock market, will return on average about 10% a year over the long run. Okay, so I know you can't walk into the bank and get 10% a year, but historical figures for the stock market say you could get 10% a year. Okay, who's going to have more money? The guy that put away 1,000 a year for like 15 years, or the guy that put away 1,000 a year for like 30 years, but one guy just started earlier. Yep.
Right, so you say,
Yeah, so he put 1,000 a year away for like 15 years and stopped. That's it. Did not put any more money in, just left it there to earn interest. The other guy started when the first guy stopped. And then he put in for like 35 years, from like age 30 to 65 or whatever, 35 to 65. So who gets more money? The guy that put away like 15,000 or the guy that put away like 35,000? First guy? How much more money?
I started earlier. Yeah, like a lot.
Okay, so here's, oops, let me drag that over. Let me drag this spread, no, drag the frame. Let me drag the spreadsheet over. All right, here we go. Okay, so here's Alex. Started at age 20, put in till age 34, so put in the 15,000. It's getting 10% a year in interest. That's the amount he has. Here's Amos starts with 1,000 and when he's 35 years old, and then, all right. So who has the most money? So when they turn 70, the guy who last put in money when he was 34 has $1,080,000, and the other guy who's been putting in 1,000 a year since he was 35 until age of 70, put away each year, has $329,000. This guy put in 36,000 in total, but started 15 years after the guy put in 15,000. He's got $700,000 more. So this is your takeaway for today. Start early.
Yeah.
Okay, so here's Alex is in orange and Amos. Here's Alex. Nothing much is happening, but eventually it starts to take off, and he's just like 20 years behind, right? So that curve is just sitting on this part. So Alex has reached the point where exponential growth is really kicking in, right? It is all exponential growth along the way, but it's like, yeah, nothing much is how, okay, and now this is really growing. And he's 15 years behind. So when he's 85, he'll have that, but this guy who needs money will have way more, okay? Because this thing's just going to keep going up like that. Any questions?